So very nice talk. I enjoyed your talk very much. Now to your conclusion, I'm wondering, even you have randomly oriented, randomly distributed bubbles, you can get doubly negative behavior, no? And my question is concerned about the behavior of the randomness. I don't believe if you have completely randomly, distribution, you will get this behavior. There must some condition.
Yes, you're absolutely right. And the condition is that we have pairs of bubbles at a fixed separation. The separation between pairs of bubbles has to be fixed. That's the key feature that really drives double negative behavior for these monopolar resonators. Because then when you have pairs at a fixed distance and you treat this bubble pair as a single scattering entity effectively, you have both a monopolar and a dipolar response out of the pair. And that's the key ingredient that we were able to show.
Okay, thank you.
Totally randomly distribute the bubbles with no correlation spatially, you were absolutely right. You just get a band gap and singly negative behavior.
Okay, thank you. And my second question is related to your experimental, realization. And for 2D extremely thin, bubble metascreens.
Yes.
The stability of the metascreen, I think, is very, very critical. I mean, if you have a very thin layer, how stable, is your thin layer?
Well, it's fine if you treat it very carefully. And it is perhaps difficult to imagine doing, coherent perfect absorber experiments, because how do you support it without it collapsing? But if the thin layer is on a rigid reflector in the SAB configuration, it can be very stable. If you have something like bubbles in PDMS, which is what we have studied.
Okay.
That's not to say that it lasts forever. If you increase the pressure in the water too much, it's not stable. But and for some reason, after a few years, our bubbles vanished one day. So it can happen, but the sample did last many years before this happened.
Yeah, it could be very, very difficult to produce, a periodic arrangement of the bubbles, no, in 2D case.
Well, these printing techniques can be useful. You need a template.
Okay.
And for our experiments in the ultrasonic frequency range, the template the bubbles had to be small, but it's probably easier for larger bubbles so long as they're not too big.
Okay. Okay, thank you. No, thank you for your comments. Thank you.
Sure.
Yeah.
Super. In my opinion, it's a little bit reminiscent of this Manchester experiment, in optics, Grigorenko et al. When they have to pair the gold nanoparticle to see the negative refraction effect. I mean, people tend to always pair things,
Yes. It's the simplest kind of spatial correlation that one can imagine, and it turns out to be extremely effective in this case.
And in fact, you can allow from some kind of randomization of the distance, between the paired bubbles. I mean, you get the same effect if it's not really always the same kind of distance,
Well, as the distance between them fluctuates, that degrades the performance. That's important.
Ah, okay. But it becomes broadband then, no? You enlarge the band.
You wash out the dynamic density, the negative dynamic density effect. That's the most fragile condition, part of the metamaterial, and that goes first. It will certainly be, you get a broad absorption band, of course, but you lose this correlation effect. So
and
yeah.
why is it so isotropic? How come it is so isotropic, this effect? You know, you have shown us that you have this negative dispersion which superimposes in all directions. How come it's so isotropic?
Well, the key starts with the FCC structure, which is the lattice here.
Okay.
And this is the Brillouin zone. And it's much more isotropic than just for a simple cubic lattice. It's almost spherical. It's not spherical, of course, but it's almost spherical. So that's a good starting point. And that's why we chose this FCC structure for our initial phononic crystal experiments as well. Now, when you add the second bubble to create the diamond lattice, then you've got, of course, the nearest neighbor bubbles are the ones in the unit cell, corresponding to the unit cell. And then this negative band turns out to be as isotropic as you would expect, as you could hope for. You can notice if you're looking at the lower band, the usual band that you get for the FCC case, it's really quite isotropic, even as you get close to the zone boundary. This is the L point, that's the closest point to the origin in the Brillouin zone, this guy. And it seems to be spread out a little bit more in the diamond case. But when you go to the second band, which does not exist for the FCC, this negative band, it turns out at small wave vectors ranging up to about here to be extremely isotropic. And then you start to see the effects of the not perfectly spherical Brillouin zone when you get to high wave vectors.
But it's a little bit surprising because you have the pairs and the fact that they are pairs of, you know, particles. Yeah, it's.
Yeah, but there, if you look at the number of pairs, as it were, number of nearest neighbors for a given bubble in the corner of the unit cell, they are in the cubic unit cell. They're at positions a quarter of the lattice constant, which I'm sorry has this funny symbol H in this case. And so if you think of the ways of going along 3D diagonal directions away from a given bubble, there's quite a lot. And so the bubble pairs are oriented in particular directions, but there's a lot of them. So I think that's a way of having some intuition as to why it should be, these effects that depend on these pairs should be as isotropic as it is.
Okay. Wonderful. And you can allow to have pairs of, bubbles with different properties. Does it help, for instance, different diameter or different kind of, constituent? I mean, did you look at this when these are not identical bubbles, isn't it?
Well, we focused on identical bubbles because that was the case that we thought would be the most striking in many ways.
Yeah.
And maybe easiest to manufacture as well.
Okay.
There's been quite metamaterials created from two kinds of inclusions.
Yes.
One having monopolar response, the other having a dipolar response. And that is an obvious thing to do, and it works. It works very well. We were trying to stick with one kind of scatterer, Keep the simplest situation that one could imagine. They're all the same size. Because then you will tend to smear things out if you have two sizes of bubbles, right? So whether you lose your sharp dipolar response, you might. So, but we haven't looked at that.
Okay, so wonderful. So please, people, ask your questions. I should be more silent. So,
You're always good at animating discussions. So.
No, but it's very exciting, you know, for someone who is not in the subject. I mean, I find this really. And what is more exciting is that you can actually model this as well with COMSOL. I'm very surprised that you can model bubbles with COMSOL. I did not know that actually. So it's
well, it's okay in ordered structures.
Yes, yes.
Because you can invoke periodic boundary conditions. But if the system is just random in COMSOL, it's very difficult. So we use COMSOL for the 2D layer. 2D is much better than 3D in COMSOL. Otherwise, with our computing resources, we risk run out of memory. You can use COMSOL for band structures, of course. And that's what Fabrice did to calculate the band structure here. But if the system is disordered, using COMSOL has great limitations. You're limited to very small samples. And on a completely different topic, when we were looking at the modes of a 3D disordered system consisting of aluminum balls, aluminum beads, with our available memory, which was not that great, we really couldn't get beyond about 30 or 40 spherical scatterers with our resources in the frequency range that we were looking. It depends on frequency too, of course, because it depends on the resolution that you need and the mesh that you set up in COMSOL.
Okay. So anyone has further questions? I'm sure you do, actually.
Maybe everybody knows this.
No, it's very interesting because we try to see if we can translate our research also in this kind of area, which is really, different, but different in terms of the physics, but perhaps in terms of the models, it's fairly easy to translate. I mean, at least when it's periodic.
Right. Well, I mean, the key point is we focused on bubbles in this talk, but the key thing is the monopolar resonances. So anything that has a monopolar resonance will have analogous effects. And so, Helmholtz resonators, for example, are a case in point. So whether we can extend it to elastic metamaterials is not so clear to me, but maybe,
And actually, Stéphane Brûlé, who is also following this talk, so he works on seismic waves. He suggested that perhaps you might have some kind of very soft inclusions added to the soil. You have already your granular soil.
Yes.
Perhaps you could envision that the soil could be assumed to be, in some cases, very soft. It's almost like a liquid in certain conditions. And then you would have these kinds of pockets, bubbles, and perhaps you could achieve similar effects to what you have described, maybe your models can be extended.
Yeah, possibly. Yeah. One needs to do the modeling and find out the character of the resonances of this soft inclusion. If one, the example that I'm most familiar with is the work of Thomas Brunet and, he's a group really. So looking at suspensions, colloidal suspensions of soft inclusions, soft, liquid inclusions, and they have a whole host of resonances. So they're not just monopolar for a liquid drop in a liquid. So you add complexity, but then maybe if you want complexity of resonances, that's a good thing. So, but the same approach can be followed, because you can figure out the scattering function for a single scatterer and build from that.
I have another naive question. Have you tried to replicate this analysis, but in the time domain? So using some time domain simulations, say with FDTD or these kinds of package. Is there any interest of doing so?
We in this work, we haven't followed that route. That's another possibility for simulations for sure. And that's what we did with Pierre Demier in our work on the steel rod phononic crystals. And, that works very well, I guess, with finite difference time domain simulations. The accuracy degrades if the sample is too thick, but it opens up another possibility that has maybe not the same limitations. So that's certainly a possibility. We haven't done it in this case.
Okay, so
I like to focus as much as possible on models, analytic models, and where that wasn't feasible, we worked on with the multiple scattering theory, which includes the multiple scattering corrections between bubbles, which is important.
This might be very interesting for your, for your lens, to see the dynamics in time of your lens, to see the image building up, perhaps. I mean, similar things have been done in the periodic case, but perhaps for you, this would add a different dimension to see.
Yeah, that's something we could do, and that we haven't done, and that's where FDTT would be useful, I think, particularly in the simulation regime. And of course, that's the way we always like to do experiments anyway with pulses. You have to be a little bit careful because pulses are intrinsically broadband, so there's a nice compromise there. So
actually, I did not pick it up. How narrow is the band of this negative slope? I mean, what is the frequency range? Is it very sharp or?
Well, it's pretty narrow. Yeah, I mean, it goes from 2.96 to 2.93, something like that. You can read it off here, right? It's just the width of this band, and this is 2.9, this is 2.95 kilohertz. So it is very narrow.
And so I guess that one of your investigations is, can you enlarge these bandwidths perhaps, and how would you do so? I mean, do you consider some kinds of supercells, or I mean, what would be the possible ideas to make it as broad as possible? I mean, I understand it's a resonance phenomenon.
It's a good question, and the answer isn't obvious to me, so I haven't really thought about that.
And how does it compare actually with metamaterials? It seems similar in terms of the sharpness of of the width of the interval. This kind of resonant periodic metamaterials which exhibit doubly negative parameters. It's always also very, very narrow. So perhaps this is why people don't really study them in the time domain.
Well, you really want to work on the dynamic mass density contribution, and you want to find ways of enlarging the negative regime of the dynamic mass density. So that would be the direction to focus on, because that's the resonance is always much sharper than the monopolar one.
Okay.
So, I have one question, Sebastian, please.
Oh yeah, please do, Yann.
Okay, sorry. I don't want to take too much time. It's a very short question, maybe a technical question. So thank you first, John, and nice to see you again.
It's good to see you, yeah.
The question is on the viscosity. When you take into account the viscosity, I suppose that you choose the shear viscosity and also the bulk viscosity with respect to the Navier-Stokes equations. Is it the case at each time when you?
Well, it's the shear viscosity that I was talking about, focusing on, because that's the one that has a big effect on the bubble resonances.
Okay. Okay, so you know already that
and we also include, you know, the longitudinal absorption, the absorption for longitudinal waves in our modeling, which involves the other viscosity.
Okay. That you don't take into account the bulk viscosity linked to the motion of the fluid in the bulk, or did you?
Yeah, that's the intrinsic. It's related to the intrinsic absorption of longitudinal waves in the matrix.
Okay.
So we're talking about the matrix viscosities in this case.
Okay.
For both bulk and shear.
And do you know which one is more important between the shear? I mean, between the solid and the fluid.
Well, it's really the shear one that's the most important for us.
Yes, it is. Okay.
Particularly for the superabsorber case.
But
this has this huge effect because it, you know, it affects the bandwidth directly, as the model shows.
Yeah. Okay.
The the bulk viscosity is just a little bonus. So if you make it the intrinsic absorption of longitudinal waves very high in the matrix, of course, you're halfway there already to start with, but that's not what we're really trying to achieve.
Okay, thank you.
Welcome.
Hello, Sebastian. Can I ask a question, please?
Yes, please do, Mohamed.
Yeah. Okay. Thank you for this nice talk. So my question is simple. It's about derivation. So did you consider like some motion for these bubbles inside the host medium, or they're considered as static?
Their positions are considered as static. So it's just the motion of the bubble surface that creates all the effects.
And,
so we're not doing experiments in which the, you know, this, for example, in our bibubble case, if you wanted to use the negative refraction effects, the best way would be to have a way of fixing the bubble pairs so that separation remains constant, but they move around and reorient and so on. With time, you could fluidize your suspension of these bibubbles, and then they'd be evolving in time, moving around in complicated ways, and you get wonderful ensemble averaging, you know, just using a digital oscilloscope and leaving it to average for a while. So that would be a potential direction where in experiments this could be really quite useful.
Okay, and like what happens if, for example, if all the bubbles, for example, are spinning in the same direction or having some coherent motion? Is it possible to consider? Or?
We haven't done so. We haven't tried to take our bubble pairs and make them rotate. I mean, sure, that could be interesting. I don't know what would happen. So.
Okay. Thank you.
Sure.
So I've got a bit of a crazy question. So there is this area of time-modulated metamaterials.
Mm-hmm.
What about time-modulated bubbles? I mean, can you kind of shake all this and, you know, generate new exciting effects? I mean, can you think of some kind of experiments?
Well, we started to look in that direction a long time ago before time modulated metamaterials and so on became trendy.
Yeah.
And one realized some of the things that one can really do. And that was, it's a little bit like some of the work in Bristol, variation on that, where they say phononic crystals, and they use a low frequency ultrasonic wave to position the scatterers, and then they can study the properties of the frequency of interest. So we were interested in moving the scatterers around, and possibly if you had a time modulated compression of the medium, then you would modulate the resonances of the bubbles, their size. And that might create interesting effects. We haven't really considered that, but that would be perhaps a way of introducing a time modulation that might have interesting additional properties, for sure. Yeah.
That's
so
very
a good
interesting.
question. Yeah.
Yeah, and this group of Bristol, it's a group of which researcher? I mean, I did not know, so.
Oh, gee, I'll have to look him up.
It's in mechanical engineering or physical acoustics or.
Well, they bridged the two areas.
Very interesting. I did not know.
It's actually a good. I mean, they've done some very nice work in the phononic crystal regime with taking scatterers, the solid scatterers, and positioning them nicely with 6 counter propagating beams to make the particles line up where you want them.
Okay.
And Valentin Leroy has also looked at the Bjerknes forces that acoustic waves can move bubbles around.
Yeah.
We had some initial experiments where we're looking at the dynamics of bubbles using diffusing acoustic wave spectroscopy. And we noted that if the incident waves were too powerful, that we clustered the bubbles together. They tended to move together and create aggregates. And that seemed quite interesting. We didn't really follow up on that. It was a little complicated at that stage to model with Bjerknes forces and so on, but it should be possible and could be quite interesting.
Super. Okay, so do we have any more questions from the audience? And like me, this can be quite naive, or this can be a more, focused question like Jan or Mohamed. Please come forward with your question, people. All right, so thank you so much, Professor Page. I think it's a fantastic talk, and hopefully we can welcome you back on a different topic, because you covered so many topics, so that,
Sure, well, I'd be happy to contribute again if I can make a useful contribution to this wonderful seminar series, or webinar series. So.
Thank you so much, John Page. Yes, you're right, Mohamed. We should really clap in our hands. It was a wonderful talk. And I just wanted to mention that, of course, Professor Page's talk will remain accessible permanently via the metamat.org webpage. And next week, we have the great pleasure to welcome Katya Bertoldi from Harvard University. Yes, Jan, you have something to say?
No, nothing else. It's a very nice presentation also for next week. I will do my best to assist also to the. So thank you, John.
Great. Well,
yes.
Thank you very much for the invitation, and thank you for listening. So
we learn a lot. It's great. These topics are really fascinating. Bubbles, soft metamaterials. I think it has a great future. And I was thinking, in terms of the group in Bristol, perhaps it was a group of Professor Bruce Drinkwater, or perhaps it's not.
Yes, you're right. You are right. Thank you. Yes.
Okay. So I know a little bit Bruce and
Yeah.
you're absolutely
We never
right.
had the
People-
opportunity to meet him, which is a great pity. But anyway, yeah,
He's-
maybe one of these years we get over the
Yeah.
current crisis.
Hopefully, but it's not yet official. Perhaps there will be an opportunity to meet in 2023 in London for a big event. Let us see. Okay, so thank you so much, Professor Page, and thank you so much, Jan, Mohamed, and so on, and people for attending. And I wish you all the best, and let's stay safe, and hopefully when we all get our double vaccination, we can resume our trips to conferences.
Great.
Okay, merci.
Allez, salut. Bye-bye.
Salut.
To that. Thank you.
Bye.
Grand merci.
Merci.
Bye bye. Au revoir.
Merci, John. Merci beaucoup. It was fantastic.
Plaisir.